Spring 1938, Baldwin Locomotive Works, Philadelphia. Blueprints covered every surface in the engineering department as draftsmen bent over drawings that defied conventional locomotive design. The Denver and Rio Grande Western Railroad had submitted specifications that seemed to contradict the fundamental laws of mountain railroading. Build a locomotive powerful enough to replace 3 helper engines on grades exceeding 4%. Make it flexible enough to navigate curves designed for smaller power. Keep the axle loading light enough for aging mountain trackage. The specifications appeared mutually exclusive. Every railroad engineering manual said the same thing. Power requires weight. Tight curves demand short wheelbases. Light axle loading means reduced tractive effort. You could choose 2 of these requirements perhaps, but achieving all 3 simultaneously violated decades of accumulated locomotive design wisdom. European railway engineers had proven this through countless mountain operations across the Alps and Pyrenees. But in a drafting room that spring morning, Baldwin's chief engineer proposed something that contradicted every rule of locomotive construction. Design an articulated compound engine using the largest practical boiler diameter, employ a 2-8-8 two-wheel arrangement that distributed weight across 8 driving axles, and create a front engine section that could pivot independently from the rear drivers. The room fell silent. It seemed impossible choosing power and flexibility simultaneously during an era when American railroads demanded proven technology. The locomotive they were about to create would operate reliably for over 4 decades in the most punishing mountain service on the continent. The secret wasn't in making it look conventional. The telegram arrived at Denver and Rio Grande Western headquarters on March 15, 1928, just weeks after the railroad's directors had approved a capital expenditure that would transform their Rocky Mountain operations. Freight tonnage through the Continental Divide was doubling annually as Colorado mining expanded and agricultural products moved eastward to Kansas City markets. The existing fleet of 280 consolidation locomotives could barely maintain 25 miles per hour on level track when hauling 30 loaded freight cars. On the brutal grades west of Salida, where the rails climbed toward Tennessee Pass at gradients exceeding 3.5%, those same locomotives needed helper engines every 8 miles, sometimes 3 helpers per train. The mathematics was crushing. Current motive power consumed 4 times the coal needed for equivalent tonnage on flat terrain. Helper operations required maintaining expensive engine facilities at remote mountain locations. Crews spent more time coupling and uncoupling helpers than actually moving freight. Most troubling, the helper shortage created bottlenecks that delayed time-sensitive shipments and frustrated customers who increasingly considered truck transport for shorter hauls. William Freeman stood in his office on the 3rd floor studying operational reports that painted an unsustainable picture. The railroad's 1930-27 operating ratio had climbed to 92%, meaning every dollar of revenue required 92 cents in operating costs. Helper operations alone consumed nearly 15% of total locomotive fuel budgets. Even accounting for every efficiency improvement in existing operations, the mathematics remained brutally simple. The Denver and Rio Grande Western couldn't compete with rival railroads using 50-year-old technology on 21st-century mountain grades. The problem traced back to simple physics that had constrained mountain railroading since the 1860s. Locomotives generated pulling force through friction between driving wheels and steel rails. That friction coefficient remained constant regardless of locomotive size, meaning increased pulling power required proportionally increased weight on drivers. But mountain trackage, particularly the aging rail installed during Colorado's mining boom, couldn't support unlimited axle loading without rail failures and accelerated tie deterioration. Baldwin Locomotive Works had pioneered articulated designs in the early 1900s, recognizing that dividing a large locomotive into 2 separate engine sections connected by a flexible joint could deliver the power of heavy engines while maintaining the curve negotiation abilities of smaller locomotives. The mallet compound design, developed by Swiss engineer Anatole Mallet, used high-pressure steam cylinders to drive the rear engine section, then routed that exhaust steam to larger, low-pressure cylinders driving the front engine. This compound arrangement extracted maximum energy from each pound of steam, improving fuel efficiency on the extended mountain grades where locomotives worked continuously at high power output. But it created a machine that looked fundamentally wrong to crews accustomed to conventional rigid frame locomotives. The specifications that Baldwin's engineers developed that spring showed a locomotive 298 feet long, from coupler to coupler, weighing 956,000 pounds, ready for service. The boiler alone measured 94 inches in diameter, creating the bulbous, oversized appearance that would prompt immediate skepticism from operating crews. Those massive dimensions housed fire tubes providing heating surface exceeding 7,000 square feet, generating steam at pressures reaching 240 pounds per square inch. The 2882 wheel arrangement distributed this enormous weight across 16 driving wheels arranged in 2 groups of 8, with each group functioning as an independent locomotive. The front engine articulated on a hinge pin, allowing it to swing laterally while navigating curves that would derail a rigid frame locomotive of equivalent length. This articulation was visible in the locomotive's profile, creating an obvious joint between front and rear sections that made the machine look like 2 locomotives accidentally welded together. Samuel Vauclin reviewed these specifications with growing concern during meetings throughout April 1930-28. Baldwin had built hundreds of locomotives, but never one combining this specific arrangement of features for sustained mountain service. The 2882 wheel arrangement had proven successful in drag freight service on gentler grades, but the Denver and Rio Grande Western needed power that could maintain 22 miles per hour on 4% grades at altitudes exceeding 10,000 feet. Thin mountain air reduced boiler efficiency by limiting combustion intensity and decreasing steam generation capacity. Water supplies at high-altitude stations often contained minerals that caused scale buildup in boiler tubes. Winter operations in mountain passes meant working in temperatures that could freeze lubricating systems and crack cylinder castings if locomotives weren't properly winterized. Most troubling were the tight curves, some as sharp as 24 degrees, that required precise weight distribution to prevent derailments when heavy locomotives entered curves at operational speeds. The culminating decision came during a board meeting at Baldwin's Philadelphia headquarters in late May 1930-28. The first L-131 emerged from Baldwin's Eddystone plant on September 12, 1930-28, rolling slowly through the erecting shop doors toward the test track where acceptance trials would determine if this ungainly machine could meet its performance guarantees. Shop workers who had assembled conventional locomotives for decades gathered along the track to witness something that looked more like a mechanical mistake than the future of mountain railroading. The locomotive's proportions violated every aesthetic principle that defined powerful steam engines. The enormous boiler, nearly 8 feet in diameter, sat atop a frame that seemed too delicate to support such mass. The front engine section jutted forward at an awkward angle when positioned for straight track, emphasizing the articulated joint that would allow it to pivot through curves. Most jarring was the visible gap between front and rear sections, a mechanical acknowledgement that this wasn't really one locomotive but 2 semi-independent machines connected by steam piping and a frame hinge. Thomas McKenna had worked as a locomotive engineer for the Denver and Rio Grande Western for 17 years, running everything from ancient narrow-gauge power to modern Pacific-type passenger engines. He arrived at Baldwin's plant that September afternoon with 3 other senior engineers selected to evaluate the new articulated before it shipped westward to Colorado. His first impression, shared candidly with Baldwin's chief mechanical officer, was simple. It looks like something a committee designed when nobody could agree. The front low-pressure cylinders measured 39 inches in diameter, creating bulbous protrusions that dominated the locomotive's forward profile. These massive cylinders, necessary for extracting power from low-pressure exhaust steam, made the front engine appear grotesquely oversized compared to the 24-inch high-pressure cylinders at the rear. The overall effect suggested a locomotive that had suffered some form of industrial accident during construction, perhaps having its front section transplanted from a completely different machine. McKenna's crew spent 4 days conducting acceptance tests on Baldwin's Pennsylvania test track, measuring drawbar pull, steam generation capacity, and mechanical reliability under simulated load conditions. The specifications claimed tractive effort exceeding 135,000 pounds, nearly triple the pulling power of the consolidation locomotives currently struggling through Colorado's mountain grades. But test track performance meant nothing if the machine couldn't navigate the operational realities of mountain railroading. The real skepticism emerged during discussions about curve negotiation. The L-131 measured nearly 90 feet from the pilot to the tender rear, longer than many passenger car consists. Railroad engineers knew from painful experience that long, rigid-frame locomotives derailed on curves when their fixed wheelbases couldn't accommodate the lateral forces generated during curve entry. The articulated design theoretically solved this problem by allowing the front engine to pivot independently, but theory and reality often diverged spectacularly in actual railroad operations. Water capacity presented another concern that became apparent during the acceptance trials. The tender held 15,000 gallons of water and 20 tons of coal, enough for perhaps 150 miles of operation on level terrain. But mountain grades consumed water and fuel at rates that could drain those supplies in 75 miles or less, requiring frequent servicing stops that would limit operational efficiency on the long climbs between Salida and Tennessee Pass. The L-131 arrived in Denver on October 3, 1930-28, transported in sections aboard Pennsylvania Railroad flat cars for final assembly at the Burnham shops. Word of the strange articulated locomotive had spread throughout the Denver and Rio Grande Western system, prompting off-duty crews to gather near the shop complex hoping to witness this mechanical curiosity that supposedly would revolutionize mountain operations. Thomas McKenna drew the assignment for the locomotive's first revenue run, a westbound manifest freight scheduled to depart Denver at 6:45 on the morning of October 18th. The consistory included 47 loaded freight cars weighing approximately 4,000 tons, normally requiring 2 consolidation locomotives plus a helper engine stationed at Dome Rock for the initial climb toward the Continental Divide. The early morning departure proceeded smoothly through Denver's industrial suburbs as McKenna familiarized himself with the articulated's peculiar handling characteristics. Steam pressure built quickly in the massive boiler, reaching a working pressure of 240 pounds per square inch within 30 minutes of lighting the fire. The compound cylinders operated with a distinctive rhythm, high-pressure exhausts pulsing from the rear drivers followed immediately by deeper, low-pressure exhausts from the front engine. The first real test came at Dome Rock, where the grade increased to 2.2% for the climb toward Palmer Lake. On conventional trains, this was where helper engines coupled on, adding power for the sustained grade work ahead. McKenna notched the throttle forward, feeling the locomotive surge against the train's weight as steam filled those massive 39-inch low-pressure cylinders. The L-131 accelerated smoothly, maintaining 18 miles per hour up a grade that normally reduced consolidation locomotives to 12 miles per hour, even with helper assistance. The articulation point between front and rear engines flexed on smoothly through the moderate curves approaching Palmer Lake, demonstrating none of the binding or wheel slip that critics had predicted would plague such a large machine on mountain trackage. But the definitive test came 28 miles further west at Tennessee Pass, where the Denver and Rio Grande Western climbed to 10,240 feet elevation through sustained grades exceeding 3.5%. This was the railroad's operational bottleneck, the place where helper engines worked continuously and where inadequate motive power meant delayed schedules and lost revenue. The approach to Tennessee Pass began at Minturn, where the track entered a canyon so narrow that curves and grades combined to create what railroad engineers called compound difficulty. Sharp curves multiplied the effective grade by adding lateral resistance to the gravitational load. On straight 3% grades, locomotives fought only against gravity. On curved 3% grades, they fought gravity plus the sideways forces generated, as wheels scraped against rail through the curves. McKenna eased the throttle wide open as the L-131 entered the approach grade below Tennessee Pass. Steam pressure held steady at 235 pounds, the firemen working methodically to maintain consistent fuel bed coverage across the enormous grade area. The locomotive settled into a steady rhythm, compound cylinders exhausting in sequence as both engine sections synchronized their power delivery against the crushing grade resistance. 22 miles per hour. That was the speed Thomas McKenna maintained through the steepest section below Tennessee Pass, hauling 4,000 tons up grades that reduced conventional locomotives to walking pace, even with helper assistance. The L-131 pulled steadily through curves that should have induced wheel slip, maintaining consistent drawbar pull that kept the train moving without the surging and jerking that characterized helper-assisted operations. The articulated joint worked exactly as Baldwin's engineers had predicted, allowing the front engine to swing laterally through curves while maintaining power delivery. The low-pressure cylinders extracted every usable calorie from the exhaust steam, creating fuel efficiency that McKenna could monitor by watching the fireman's workload. On a conventional locomotive climbing this grade, the fireman would be working continuously, shoveling coal desperately to maintain steam pressure. Here, the fireman worked at a sustainable pace, adding fuel methodically because the compound system used steam so efficiently. At 10:19 that morning, the L-131 crested Tennessee Pass without helper assistance, becoming the first single locomotive to haul 4,000 tons over the Continental Divide since the railroad opened this route in the 1880s. The achievement meant nothing to abstract railroad statistics, but everything to practical operations. It meant one locomotive doing work that previously required 3. It meant eliminating helper facilities at multiple mountain locations. It meant faster schedules, reduced fuel consumption, and operational flexibility that could transform the economics of mountain railroading. Word of the successful Tennessee Pass run reached Denver headquarters before McKenna completed his westbound trip to Glenwood Springs. William Freeman immediately ordered performance testing that would document the L-131's capabilities under controlled conditions. Railroad engineers needed hard data about tractive effort, fuel consumption, and sustained grade performance to justify ordering additional articulated locomotives. The testing program extended through November 1928. Subjecting the L-131 to every operational condition it would encounter during regular service. Engineers measured drawbar pull on 4% grades, documenting tractive effort exceeding 138,000 pounds. They recorded fuel consumption across multiple trips, showing the compound cylinders reduced coal usage by 32% compared to helper-assisted operations using conventional locomotives. Most importantly, they evaluated mechanical reliability under sustained high-power output. Mountain grades meant locomotives worked at maximum capacity for hours continuously, creating stresses that exposed any weakness in frames, running gear, or steam systems. The L-131 operated flawlessly through these tests, showing none of the bearing failures, frame cracks, or cylinder problems that plagued locomotives pushed beyond their design limits. The tight curve tests at Glenwood Canyon provided the most dramatic validation of Baldwin's articulated design. Railroad engineers had identified a 24-degree curve where conventional long locomotives occasionally derailed when hauling heavy trains. The test protocol called for approaching this curve at operational speed with maximum tonnage, creating the most demanding lateral loading the locomotive would experience in regular service. The L-131 negotiated the curve smoothly, the articulated front engine swinging laterally exactly as designed. Post-test inspection showed no unusual wear patterns on wheels or rails, confirming that the articulation distributed lateral forces without exceeding the strength limits of track structure. The success of the initial L-131 prompted immediate action from Denver and Rio Grande Western management. In December 1928, the railroad placed orders for 9 additional articulated locomotives, designated Class L-131 through L-141, representing the largest single motive power investment in the company's history. Baldwin delivered these additional locomotives throughout 1929, each incorporating minor refinements based on operational experience with the prototype. Later units featured improved lubrication systems for mountain winter service, reinforced articulation hinges to handle sustained high-stress operation, and modified ash handling systems that simplified servicing at remote mountain terminals. As the fleet expanded, specific locomotives became associated with particular crews and routes. L-134, assigned to the Tennessee Pass pool, became known among enginemen for its exceptional steaming capacity that maintained pressure even on the longest sustained grades. L-137 developed a reputation for smooth operation through tight curves, making it the preferred engine for crews working the tortuous trackage through Glenwood Canyon. The operational transformation these locomotives enabled became apparent in traffic statistics compiled throughout 1930-29 and 1930. Freight tonnage through Tennessee Pass increased 43% without adding track capacity or helper facilities. Average freight train speed increased from 14 to 21 miles per hour on mountain grades, reducing crew hours and improving equipment utilization. Most significantly, helper locomotive requirements decreased 78%, allowing the railroad to redeploy those locomotives to other duties or retire aging power that had become maintenance-intensive. Thomas McKenna, who had initially doubted the ungainly articulated, became one of its strongest advocates after 18 months running L-131 across Colorado's mountain grades. He testified at railroad industry conferences about the operational advantages of articulated power, emphasizing not just the obvious pulling capacity, but the subtle benefits of compound operation. The efficient steam usage meant locomotives could operate further between water stops. The distributed weight reduced track maintenance by spreading loads across multiple axles. The flexible wheelbase minimized wear on curves, extending rail life on the severe mountain trackage. By 1930-32, competing railroads began ordering similar articulated locomotives for their mountain divisions, recognizing that the Denver and Rio Grande Western had solved problems that plagued every mountain railroad. The Norfolk and Western Railway ordered Class Y6B compounds for coal drags in the Appalachian Mountains. The Southern Pacific Railroad developed cab-forward articulateds for Sierra Nevada service. The Chesapeake and Ohio Railway acquired massive H8 articulateds for Allegheny Mountain operations. But the L-131 class retained a special status among railroad historians and locomotive engineers because it represented the first successful application of large articulated power to sustained mountain grades exceeding 3%. Earlier articulated designs had proven successful in gentler territory, but the Denver and Rio Grande Western's Rockies service demanded capabilities that pushed steam locomotive technology to its practical limits. The locomotives continued operating through World War II, hauling unprecedented tonnages as military freight moved across the Continental Divide. They survived the post-war transition period when many railroads began dieselization, remaining economically competitive because their fuel efficiency and maintenance costs compared favorably with early diesel-electric locomotives attempting similar mountain service. The last L-131 class locomotive operated in regular revenue service on August 14, 1955, pulling a westbound freight over Tennessee Pass 27 years after Thomas McKenna's initial skeptical evaluation at Baldwin's Philadelphia plant. The locomotive that crews had laughed at for its awkward proportions and strange appearance had outlasted dozens of supposedly superior designs, proving its worth through 3 decades of relentless mountain service. Preservation efforts saved several L-131 class locomotives from scrapping, recognizing their historical significance to American railroading. L-134 resides at the Colorado Railroad Museum in Golden, maintained in operational condition and occasionally operated for special events. L-137 sits on display at the National Railroad Museum in Green Bay, Wisconsin, where visitors can examine the articulated design that revolutionized mountain freight operations. The engineering principles that made the L-131 successful influenced locomotive design far beyond the Denver and Rio Grande Western Railway. The articulated compound arrangement became standard for heavy freight service on the railroads operating in mountainous terrain. The 288 two-wheel arrangement proved optimal for balancing tractive effort with curved negotiation ability. The emphasis on efficient steam usage through compound cylinders established performance benchmarks that influenced locomotive specifications for 2 decades. Modern railroad historians studying the transition from conventional to articulated power point to the L-131 as a pivotal design that proved unconventional engineering could solve problems that defeated traditional approaches. The locomotive succeeded precisely because its designers ignored aesthetic conventions and focused exclusively on functional requirements. The oversized boiler generated the steam volume needed for sustained mountain grades. The articulated frame allowed that massive boiler to navigate curves impossible for rigid locomotives. The compound cylinders extracted maximum energy from each pound of coal, creating operational economy that justified the higher initial capital cost. The human element remained central to the L-131's success story. Thomas McKenna and hundreds of other engineers, firemen, and maintenance workers learned to operate and maintain these complex machines in conditions that would have destroyed lesser locomotives. They developed operational techniques that maximized the articulated's advantages while compensating for its limitations. Their experience demonstrated that successful technology requires not just sound engineering, but also crews willing to master unfamiliar equipment. The legacy extends beyond preserved locomotives and historical records. Modern diesel-electric locomotives operating over Tennessee Pass still follow grades originally designed for steam power, including the brutal climbs that the L-131 conquered without helper assistance. Railroad engineers still study the operational economics that made articulated power successful, applying those lessons to contemporary freight operations where efficiency determines profitability. The locomotive everyone laughed at became the locomotive everyone copied. The ungainly machine that violated aesthetic conventions established functional standards that defined heavy freight operations for the steam era's final decades. The L-131 proved that sometimes the most effective solutions look wrong until they demonstrate results that conventional designs cannot match. In the end, the mountain that couldn't stop it wasn't Tennessee Pass or the Continental Divide, but rather the mountain of conventional wisdom that insisted powerful locomotives couldn't navigate tight curves, that articulated designs were too complex for reliable service, and that prioritizing function over appearance would never gain acceptance from practical railroad crews. The L-131 conquered all those mountains by simply doing the work it was designed to do.